The Set Theory Guide for Artists podcast. Back for more. So what is the Set Theory Guide for Artists? Well, I already told you in the first episode, so why don't you go back and just watch it? Oh, what's that now? Okay. What's this? Viewer complaints. Terrible, stolen, inconsistent accent. Unfriendly? Well, I'm sorry if the way that I speak offends you. I'll try to be more friendly. Now, where were we? Ah, yes. Infinity, Chapter 1. The Set Theory Guide for Artists, Chapter 1, Part 1. Pack your bags for the trip of a lifetime. Continued. The real numbers. Observe the diagram below and see that there is a one-to-one correspondence between the real numbers and the unit interval and the real line and the real numbers in the entire real line, from negative infinity to infinity. So we have 0, 1, wrap it around, draw a line through. The unit interval is wrapped into a circle and placed on the real line, centered at 0. Any point in the top half of the circle is mapped uniquely to a point on the real line, outside of the circle, the green dots. Any point in the bottom half of the circle is mapped uniquely to a point on the real line inside of the circle, the blue dots. And points on the dividing line are mapped to each other, in the red dot. Every real number in the unit interval 0, 1 can be written as a decimal. R equals d sub 1, d sub 2, d sub 3, so on, where di is a natural number for all I. Georg Cantor was the first to show that the real numbers are not countable. There is no one-to-one correspondence between the real numbers and the natural numbers. Suppose the real numbers were countable, then 0, 1, the interval 0, 1 is countable. We will run with the idea that the reals are countable until we hit a contradiction. Once we hit a contradiction, this tells us that our initial assumption that the reals are countable is false. If 0, 1 is countable, let us index the reals in this interval with the natural numbers using the one-to-one correspondence between them. So r sub 0 is 0.d sub 0, 0, d1 sub 0, d2 sub 0, d3 sub 0, and so on. R1 is 0.d0 sub 1, d1 sub 1, d2 sub 1, d3 sub 1, and so on. R2 is, and so on, R3. By the one-to-one correspondence, every real number in 0, 1 is on the list. Some numbers may have more than one decimal expansion. We choose one for each real. We will construct a real number, r star, in 0, 1, which is not on the list. To make sure that we don't accidentally construct a real, which is just an alternate decimal expansion for a real already on the list, let us avoid using the number 9 in our construction. We want to ensure that our new real, r star, is different from each real on the list. Let us choose the first digit to be different from the first real on the list, on the first digit. Choose the second digit to be different from the second real on the list, on the second digit. Choose the third digit to be different from the third real on the list, on the third digit, the third digit of r star, and so on. And we can see at D00, D0 sub 0, we're going to make that different in r star. In the yellow digit, we're going to make, as long as E1 is different from D11, and the red circle, as long as E2 is different from D sub 2, 2, and so on. So r star is going to be 0. Point E1, E0, E1, E2, E3, where E0 is not equal to D sub 0, 0, E1 is not equal to D11, E3 is not equal to D33, E sub n is not equal to D sub n for all n and n. Each digit of r star is a natural number, not equal to 9, and so r star is in 0, 1. It's just some decimal 0 points. However, r star is not on the list because it is different from the nth number on the nth digit. We have reached a contradiction. The list contains all the reals in 0, 1, and yet r star is in 0, 1, but it is not on the list. Thus 0, 1 is not countable, and thus the set of real numbers is not countable. The set of reals is infinite, but it is not the same size infinity as the set of naturals. To express this, we write the cardinality of R is greater than the cardinality of N, and say the cardinality of the real numbers is greater than the cardinality of the natural numbers. Any infinite set which is not countable is called uncountable. The real numbers are uncountable. The set of real numbers is called the continuum. The cardinality of the continuum is written C equals cardinality of R. In general, two sets A and B have the same cardinality, written cardinality of A equals cardinality of B, if there's a one-to-one correspondence, aka a bijection, aka a one-to-one and onto function between them. Cantor showed that the set of algebraic numbers, roots of polynomials with integer coefficients, is countable, and thus there are uncountably many transcendental numbers, such as pi and e. Let us go back to the infinite binary tree. The infinite binary tree has countably many nodes. Each path in the tree corresponds to a subset of the natural numbers. Hence, the cardinality of the set of paths in the binary tree is equal to the cardinality of the power set of the natural numbers. By writing each number in 0, 1 as a binary decimal, aka an infinite binary sequence, we can see that the cardinality of the real numbers is equal to the cardinality of the power set of the natural numbers, written 2 to the omega. The cardinality of 2 to the omega equals cardinality of the power set of n, which equals the cardinality of the reals. If A is a finite set with cardinality of A equals n, then the cardinality of the power set of A is 2 to the n for finite. Thus, in the finite case, the power set of a set is always larger than the set. This is also true in the infinite realm. We saw that the cardinality of the power set of the naturals is strictly larger than the cardinality of the natural numbers. Cantor showed so cardinality of 2 to the omega is greater than cardinality of omega with the diagonalization. Cantor showed that in general a power set is always has a greater cardinality than the original set. And so taking power sets is a way to get bigger and bigger cardinalities. Cantor's theorem: for any set A, the cardinality of the power set of A is greater than the cardinality of A. This is Yek's proof. Proof of Cantor's theorem. Let A be a set and suppose that there is an onto function, f from A to the power set of A. Let B be the set of x in A, such that x is not an element of f of x. This is an element of the power set of A. B is the set of all x in X, such that x is not an element of the image of x under f, which is a subset of A. Since f is onto, B is a and B is a subset of A, and hence in the power set of A, there must be some t in A such that f of t equals B. Let us look more closely at this element t in the domain of f. We might ask ourselves whether t is an element of B. Then we are in the strange situation where t is in B if and only if t is not in f of t, which equals B. That is, t is an element of B if and only if t is not an element of B. The contradiction reveals that f cannot be onto. Thus, there cannot be a one-to-one correspondence between A and P of A, the power set of A, because there is no onto function between A and P of A. Thus, we have that the cardinality of the power set of A is strictly larger than the cardinality of A. Cantor gave names to the infinite cardinalities, aka the alephs, starting with the first infinite cardinality, the cardinality of the natural numbers, aleph naught, and then aleph 1, it's the first uncountable, aleph 2, so on, aleph sub omega plus 1 indexed by the ordinals. The alephs are indexed by the ordinals. We have that the cardinality of n is equal to aleph naught. If the cardinality of the natural numbers is the first aleph, and the cardinality of the real numbers is greater than the cardinality of the natural numbers, which aleph is equal to the cardinality of the real numbers? The cardinality of the real numbers is a central question in the study of set theory. Cantor proposed the continuum hypothesis, CH. The cardinality of R is aleph 1. It turns out that the cardinality of the real numbers can be different alephs in different mathematical universes. This is the topic of Chapter 6, independence of CH using a technique called forcing. This is the topic of Chapter 5, forcing. Orderings. Observe the following orderings. How could you describe the relationship between the pink and green points in the image? What role does the blue point play in each image? Okay. So you might look and say, how would you compare pink and green here? Pink, the green's a little to the left. Maybe if you had to order them, maybe that one's first. Over here we see pink and green. How could you compare them? They're kind of like on different places, hard to compare them. And then the last one, maybe that one seems like a green seems to be above the pink, or the pink is above the green, however you're oriented. The first image depicts a linear ordering where the green point is less than the pink point, while the blue point is greater than both. The second image depicts a partial ordering where the pink and green points are incomparable, while the blue point is greater than both as the greatest element. The third image depicts a linear ordering where the pink point is less than the green point, while the blue point is less than both as a least element. Consider the ordinal 4, which is ordered by the element of relation epsilon. See 0, 1, 2, 3. 0 is an element of 1, 1 is an element of 2, 2 is an element of 3, 3 is an element of 4. A well-ordering is a linear order where every subset has a least element. The ordinal 4 above is well-ordered by the element of relation. A relation that is very close to the element of relation is the subset of relation. A is a subset of B if X in A implies X is an element of B. Notice that in the ordinal 4, every element of 4 is also a subset of 4. For example, all of the elements of 3 are also elements of 4. This property of a set is called transitive. A is transitive if every element of A is also a subset of A. In general, an ordinal is a transitive set that is well ordered by epsilon. Consider some of the transfinite ordinals we've seen so far. Omega, omega plus 1, omega plus 2, omega plus 3. The limit of these ordinals is the ordinal omega plus omega, which is omega times 2. Then consider the transfinite ordinals, omega times 2, omega times 3, omega times 4. The limit of these ordinals is the ordinal omega times omega, which is omega squared. By adding, taking limits, multiplying, and taking exponents, we can reach the higher ordinals. In the finite realm, we have that every positive integer has a unique prime power factorization. In the transfinite realm, we have that every ordinal can be written uniquely as what looks like a polynomial in omega. This is Cantor's normal form theorem, which says that if alpha is an ordinal greater than 0, then alpha can be written uniquely as alpha equals omega to the alpha sub 1 times m1 plus omega to the alpha sub 2 times m2 plus, and so on, omega to the alpha sub n times m sub n, where the powers are ordinals in decreasing order and the m sub I are natural numbers. Some ordinals are special because any ordinal less than them has a smaller cardinality. An ordinal that is the first of its cardinality is called a cardinal number. For example, omega is a cardinal number. We have to wait for a long time to see another cardinal number. Each of the ordinals below is still countable. Omega squared, omega to the omega, omega to the omega to the omega, plus 100 times omega to the omega to the 10th, omega to the omega to the omega to the omega to the omega. To get to the next cardinal number, get to the next cardinality. The alephs are the higher cardinalities, so each cardinal number corresponds with an aleph. Below we write alephs with their ordinal names. Aleph sub naught is omega sub 0, or omega naught, omega sub 0 equals omega. Aleph sub 1 is omega 1. Aleph 2 is omega 2. Aleph omega is omega sub omega. Aleph alpha is omega alpha. The cardinality of any ordinal strictly between omega sub alpha and omega sub alpha plus 1 has the same cardinality as omega sub alpha. You can see in the picture that the red parts they all have cardinality omega sub 0, and then all the orange, they all have cardinality omega sub 1 until we get to omega sub 2, and so on. Ways to get bigger. Cantor's theorem tells us that the cardinality of the power set of a set is strictly greater than the cardinality of the original set. But how much bigger is a power set? The cardinality of the continuum is the cardinality of the power set of the naturals, aka the cardinality of the reals. The continuum function is a map from a cardinal number to the cardinal number of its power set. So f of kappa equals 2 to the kappa. Below are two of the many possible patterns of the continuum function. Do you have a preference? The one on the left looks very nice. The first image above is the pattern of the continuum function if the generalized continuum hypothesis holds. 2 to the aleph sub alpha equals aleph sub alpha plus 1, so the power set's the next cardinality, holds for all alpha. We'll sometimes assume that the GCH holds in order to make our calculations easier, especially later in the chapters 7. Besides taking power sets to get bigger cardinalities, there are conceptual ways to reach higher cardinalities. For example, if we think about omega and how it is a limit cardinal and how it's bigger than any power set below it, we might eventually wonder if there is an uncountable version of omega. This is the idea of an inaccessible cardinal. An inaccessible cardinal shares key properties with omega, but it is an uncountable version. An inaccessible cardinal is a large cardinal, and there are many such conceptually inspired cardinals. We will see more large cardinals in chapter 4. Other must-have books to pack for the trip. Okay, so Yek's set theory. I've used Yek a lot. A lot of the proofs are from Yek, and I should be really clear about that. And Proof in the Art of Mathematics by Joel David Hampkins is a great book. And it helps think about how to write a good proof. And it's very like a readable, it's an inspiring book for sure. Okay, what would I like to say about this? I would just like to say that, yeah, a lot of the proofs are coming from Yek right now. And I would also like to say that each chapter, I'm going to have a different outfit on that's inspired by maybe some people on this wall. And so this is Emmy Noether over here, helped Einstein, and a great teacher we read about, and an amazing mathematician. And so she sort of has like a Victorian kind of outfit look, and I like that. There's also Sonia Kovalevskaya, who I'm not sure if I'm off the screen, but she is, I think, the first woman to get a PhD in math in Europe. And she inspired me a lot when I was an undergraduate because I read, maybe I was actually a grad student by then. I think I actually was a grad student by then. There's a book, like a biography of her, and she's like sitting by candlelight and like studying, and so cozy, and she just studies every day. And she's really inspiring. And she has a really Victorian like outfit on. And also, if you can see, Hilma Off Clint is here too, amazing artist. And like, maybe she knew some logic or something. I feel like Hilma, did you know some logic or something? Amazing artist, and she has a very Victorian look on. And I kind of like this necklace thing that I didn't quite get. And so I've always like wanted to wear a red velvet Victorian outfit. So I thought this would be a great opportunity to do so. And this is like, there's like a bustle in here, if I don't know if you can see. So I rented this from Ibsen Costume Gallery. And I also have some Victorian shoes on that you can't see, but I got those because I like them so much, so I'll wear them with other outfits. So thank you for coming today. See you in 2 weeks.